Thank you, Peter and Anne, and the Atmospheric Sciences section for inviting me to present this lecture today. It's really quite a great honor, as Peter has already said. And so we don't run short of time, I will move right into the talk here. As Peter said, I'm going to be talking about tropical convection today. This is a long-standing problem in meteorology that's consumed a lot of our attention since for a long time. And I'm learning how to do the controls here. This presentation today is going to be of a historical and personal nature. The progress in understanding tropical convection has come from a combination of three really great, gigantic field campaigns, one in each of our major oceans, the Atlantic, the Pacific, and the Indian Ocean, and also along with the evolution of meteorological satellites. And I've been involved in both of those, and in fact, people tell me I'm the only living veteran of all three of these field campaigns. So I thought it would be fun to organize the talk largely around those field campaigns. We start before satellites, long before satellites. Since the beginning of time, really, people have been able to look at clouds with their own eyes. And in the 19th century, people started to give these clouds names. And we're going to be looking at convective clouds, which include the small cumulus clouds that you see there in the lower foreground, cumulus congestus clouds, which are the larger convective clouds, or I should say medium size, and then the very large cumulonimbus, which produce these well-known anvil structures or thunderhead structures that extend out from the deep precipitating part of the cloud. Then in the 20th century, we begin to have a lot of sounding of the atmosphere by balloons using radiosondes. And for the first half century, this information accumulated. And in the 1950s, Joanne Simpson, who was then Joanne Malkus, and Herb Reel put together this well-known diagram here, which shows that, these soundings showed that this quantity, which is plotted here, is called the moist static energy, which is a quantity that's conserved as parcels move around in the atmosphere. It involves sensible heat, latent heat, and potential energy. The point is it's conserved, and what they noticed was that it was maximum in the lower and upper atmosphere in the tropics, but in the middle levels of the tropics it was a minimum, and it was a mystery at first how the high moist static energy air could get up to the upper levels, and they postulated what is now known as the hot tower hypothesis, which says that the transport takes place in the clouds themselves, in the deep cumulonimbus clouds. Updrafts carry this moist static energy up to the upper troposphere, and this hot tower hypothesis is generally accepted in principle today, although the details are still very much a subject of some discussion and debate as to how it all works. So we, after the radiosonde era, then the first satellites went up. The first satellite was launched in 1960. That is first weather satellite, Tyros 1. And this was actually the first satellite picture from space. It's kind of hard to, I'm not sure exactly what we see there, except I can see there's a lot of clouds in it. And it's global, that's the main point. So this opened a whole new era of global observation of clouds, which was not possible before that. There were other things going on around 1960. This was still the era of the Cold War. And President Kennedy and others in high places were looking at ways for countries like the U.S. and USSR to cooperate in some constructive way. And I suppose it occurred to them that the weather is of interest to everybody, Russians, Americans, everybody wants to know what the weather's going to be, and to do that requires international cooperation since the weather didn't respect any national boundaries. So this was actually from a speech at the United Nations, and Kennedy pointed out that atmospheric sciences require worldwide observation and hence international cooperation. It was the international cooperation that, of course, was of main interest to him. Although Jules Charney always said it was because Kennedy was a sailor and he was interested in the weather, but I think Charney just made that up. Another thing that was going on in the early 60s was Ed Lorenz was thinking a lot about predictability, and this is not the quote you usually see from him, but you can tell from it what he was thinking, that he was recognizing the sort of limits of predictability in the atmosphere, and could see that there was a promise for global forecasting, and if this was going to be done with out to the limits of predictability, which could conceivably out to 1 or 2 weeks, that global observations needed to be improved, particularly over the oceans, and particularly over the oceans was one of the reasons for that is because it was recognized already that tropical convection was one of the major uncertainties that was affecting predictability. So with all these forces going on, the promise of global prediction, new satellite observations over the globe, and this desire for détente among the nations, which, by the way, provided financial support with that kind of motivation. This led to the Global Atmospheric Research Program, and the Global Atmospheric Research Program's first big effort was a campaign to try to understand better tropical convection via a field experiment called GATE, which is the Global Atmospheric Research Program, Atlantic Tropical Experiment. Still stands as the largest of the field campaigns, and it also is a beginning of this era of major field campaigns over the oceans in the satellite era. Now, GATE was over the Atlantic Ocean, 1974. You can see from the box there that it was aimed at the tropical Atlantic with focus on the region marked by the X. The other thing you notice here on the left is that the project had a logo. And one thing about this era of field campaigns that we know now is that every project has to have a logo because T-shirt sales are very important to field projects. And in GATE, what was on people's minds then was the fact that clouds were small and the grid elements in global models were rather large. They were the order of 100 kilometers, which is much greater than the size of many convective clouds. So this led to this thinking about the population of convection in terms of what could be predicted on a global model grid scale, and led to the idea of a small area assumption, that the clouds are small in area compared to the global model grid size, and that therefore the problem could be viewed as a statistical equilibrium between the convection and the large-scale events, and that and this is how air would get transported out of the warm, moist boundary layer and on up to the high levels of the atmosphere. That was the working hypothesis during the planning of GATE. But these satellite observations that were going on at the time produced what I really like to call an inconvenient truth, just because it sounds funny. And it was an inconvenient truth. This is a typical satellite picture. See, the problem was the satellites were, while people were talking about this small area assumption, the satellites were showing that the clouds are actually, a lot of them in the tropics are actually pretty large, what we call mesoscale, hundreds to even 1,000 kilometers across, which of course didn't fit the idea of a small area. But the planners of the experiment issued this statement and planning document from the National Academy. No particular significance is attached to the interaction between the mesoscale and the other scales. And that statement, I think, really stuck in my craw. When I was a brand new assistant professor, I was looking at this and thinking, this really can't be true. So it pretty much spent the next 40 years chasing down this problem. But nevertheless, the project went on with kind of a neat little package of ideas that sort of took care of everything. You'll notice in this picture there's a big a thin canopy of cirrus cloud emanating from the top of the hot tower, and that was the way they kind of got around this in the planning. They said, well, really, there is this thin veil of cirrus that's put out by the deep clouds, but it covers up the population, which really does look like a lot of small area plumes coming out of the boundary layer. And so this explained the satellite pictures, retained the hot tower notion, and included the smaller clouds. So it was a neat package, kept everything in there. So the experiment was planned pretty much with this hypothetical view of the cloud population in mind. GATE was the grandest field campaign. It's 1974. This was done on a scale that's unimaginable now. These were the platforms, 40 ships, 12 aircraft, and 16 sounding sites located on ships. Think of the cost nowadays to do that. The problem is the technology was still relatively primitive to what we have now. There were also 4 radars on ships, and these radars ended up playing a pretty important role. They were there to measure the rainfall within this hexagon of ships. You'll notice that around the edges, the ships are USSR ships, and the ships in the center are a mix of countries, USSR, USA, Germany, Canada. So it was truly a very fine international effort. But what came out of all of this? The radars played an interesting role here. They're the ones that came up with the second inconvenient truth. So this, I showed you the pre-gate view of the cloud population. This is a post-gate view of the cloud population. And the key features here, first of all, the hot towers are still in the picture. Now, how extensive they are, how much effect they really have, and how they actually work are all still topics that we're talking about. But they were there. There's deep convection. But more importantly, a lot of the rain is dominated by what we call now mesoscale convective systems, this scale that nobody thought was important. And furthermore, these mesoscale systems have a structure of their own. They have these extensive regions of cloud with a higher base, sort of mid-level cloud base. It's more stratiform. The rain is lighter, but it covers a much bigger area. There's upward motion aloft, downward motion below. And these things are the scale of the model grid. So it didn't really fit the small area. They don't really fit the small area assumption very well. So what came out of this sort of jumped to the kind of bottom line of GATE. We learned a lot about the heating and cooling processes in a mesoscale system, which in turn affect the larger scale. And the key things here, these systems have their convective components or stratiform components. The convective part has deep updrafts and heating through the whole troposphere, and the stratiform regions have cooling by melting and evaporation of precipitation particles in the lower levels. These systems, with their big thick animal clouds, also have radiative implications that Peter and Graham Stevens and others wrote about many years ago, and are still important to think about. But I'm going to move ahead here and look at sort of how that all summarizes. The convective region has a heating profile that has a maximum somewhere in the mid-troposphere and heating at all levels, net heating. The stratiform region, though, has this cooling at lower levels and warming at the higher levels. And so if you get a mix of convective and stratiform together, you get different combinations. The more it has a stratiform component, the more the maximum of the heating get raised to higher levels, and you get more cooling at lower levels. So this shows how it would come out if you did mix different proportions of stratiform in with the convective, and you can see it makes the heating profile what we call more top-heavy. The more stratiform gets into the picture. does this matter? That's, of course, the question that comes from this. And we did an exercise. Now we get used to some of the modern satellite data. With TRMM, we know the global precipitation pattern. And using this global precipitation pattern and then attaching a heating profile to it that assumed zero stratiform precipitation and letting a simple climate model run out to steady state, we got steady state circulation at 250 millibars. It looks like what you see here. These are the stream function lines. And you don't need to know too much about what those mean except to compare with the next figure. And the colors here show the heating associated with the precipitation, the heating that would be located at 400 millibars, which is moderately high up in the troposphere. If we go to a situation with 40% stratiform, there's more heating at the upper levels, and the circulation gets stronger. So it's just a simple indication that the heating is indeed associated with the stratiform portions of these mesoscale systems is an important factor globally. Well, I said this gate was the beginning of an era of field projects. There are many more. You can see where they've been conducted throughout the tropics. The three big ones. We've talked about GATE. There's also in the Pacific Togo Core, which was in 1992. That was led by none other than Peter Webster, who introduced me, and his colleague Roger Lucas at University of Hawaii. This was another big and very successful project. This is where it was located, over the warmest water in the West Pacific. The outer hexagon interquadrilateral has vertices where soundings were located. There were not as many facilities in this project, but we had higher levels of technology. And in particular, we had Doppler radars at this point, which goes beyond what we did in GATE. And we also had a lot of Raywensons. And I'm going to talk first about those just briefly. Also we had an official logo. T-shirt sales were good. And with the soundings, Dick Johnson did what I think is a really just brilliant analysis of the sounding data from Togo Core, where he showed that instead of a rather continuous spectrum of cloud sizes in the tropical cloud population, there's a certain importance to the middle-sized clouds, the cumulus congestus or small cumulus clouds, the middle-sized ones that make them especially important, and they constitute a little mode in the distribution. And this is something that hadn't been recognized before. It was confirmed by ARM radar observations at Manas, which was actually located close to where Togo Core was held here. The same location, similar location. And you can see from that there's a mode in the middle there that corresponds to the middle-sized cloud. So this trimodal distribution was one thing that came out of Togo Core. The other thing is we spent a lot of time again looking at the deeper convection and the more mesoscale systems. We did this in the context of the Madden-Julian oscillation, which in this region is a very prominent feature at the time of year we were out there, which was November through February. There were two passages of the MJO, as it's called, and Wheeler and Hendon developed a way to objectively identify the MJO from satellite and wind data. There are other methods, but we use theirs here. These numbers correspond to different phases of the MJO, and the dark shading is where the deep convection is, and over the Togo Core region of the West Pacific, this is longitude running on the bottom scale there. Over that zone, the active phases are this 5 and 6, and we got a lot of observations during those phases. This is an idealization of the low-level flow pattern that you would see in a kind of idealized MJO. It's a combination of Kelvin wave, east-west Kelvin wave convergence, and Rossby wave, which produce these Rossby wave, which produces these counter-rotating cyclonic gyres on either side of the equator. The dots here and the numbers show the days and locations where, relative to the flow pattern, where we got radar data, and from this region from the Kelvin wave convergence and then on into the first part of the Rossby gyres there, where the westerly winds are very strong, we obtained a lot of dual Doppler radar observations, or a lot of Doppler radar observations. And one of the things they showed is a very marked similarity to a model of tropical convection that's been advocated for many years by Mitch Moncrief, where he points out that it's a natural behavior of the atmosphere to adjust on the mesoscale to the wind shear in the environment and the stability in such a way that the overturning occurs in a deep layer. You can see that with the pink shading there, the updraft is a deep layered feature, and the scale is not exactly shown, but it would be over 100 kilometers or so, a very broad thing. And then there's also a layer of downdraft air entering below that, and that lies between flows going the two opposite directions. And we saw that structure over and over again in the Togo core radar observations. This shows a result that we concluded from 25 flights around the convective regions of mesoscale systems in Togo core. If you're really sharp-eyed, you'll notice that I have the inequality going the wrong direction there, but otherwise the figure is good. And the main thing it shows here is a deep layer of inflow, anywhere from 1/2 to 5 kilometers or even more deep. So it's not just plumes rising out of the boundary layer anymore. It's this deep layer of inflow. And we also, with 25 other flights around stratiform regions, we were able to determine that had this 3-layered flow structure with mid-level flow entering, subsiding between the two flows going the other direction. So again, we saw some confirmation of the Moncrief type of structure. And so what that did was allowed us to add to this model of the mesoscale systems that we got from GATE. We know from Togo core they have this deep layer of inflow at lower levels, which feeds the updraft structure, which reaches up to the upper troposphere, and then it also has a mid-level inflow coming in below the anvil cloud and feeding into the stratiform region. So now after Togo core, we had learned a lot, not only about the heating structure, but the momentum structure of these systems, and these structures do have implications for momentum transports, which we don't have time to go into here, but they do. So that brings me finally to the most current of the three great field experiments. Dynamo, which occurred in the Indian Ocean, that's the middle one there, from late 2011 to early this year, 2012. This project was led by Chidong Zhang and Chuck Long and Kunio Yoneyama from Japan. Another very successful project involving a lot of facilities, but even fewer facilities than Togo core, but even higher technology. So the number of facilities has gone down, the technology has gone up. So maybe some compensation there. The layout of the project is here. The project took advantage of 4 islands to locate soundings that were taken every 3 hours. Dick Johnson, again, involved in leading the sounding effort. And 2 ships, the U.S. ship, the Ravel, the Japanese ship, the Mirai, and they formed these 2 quadrilaterals, which are useful for examining the sounding data. I want to focus here on there's lots of coming out of the sounding data. Lots is also coming out of oceanographic measurements from the ships, and I don't have time to cover all of that. Mainly focusing on the clouds, so I'm going to focus on the radars. Notice there were 4 radars at the station on the upper left, and there were 4 radars, 4 different kinds of radars. 2 radars on each of the ships, and then at the lower left station there, which is Diego Garcia, the P-3 aircraft had airborne radars. So there was a lot of radars we threw at this problem this time. And another logo. This one, oh, by the way, Dynamo has a lot of names. Dynamo, Amy, Cindy. There were many arcane, bureaucratic, interagency reasons for having 3 different names. but anyway, we managed to get the logo written in the native Devehi language, so that sort of hides the naming problem, and produces a very nice logo again for this project. Again, good T-shirt sales. The focus of Dynamo and Amy, a little different from the earlier two projects in that the focus was really on the whole population of convection more than the individual cloud systems. And obviously this is only a year after the project, so it's early to be saying too much about what we found, but I'll show you some results, and I'll also show you here the general approach that we took. This again is this picture of a typical tropical cloud population. Again, we used centimeter wavelength radars to measure and detect precipitation in 3 dimensions, just like we did in GATE. As we did in Togokor, we have a lot of Doppler radar observations to go with the precipitation observations. But in Togokor, we brought in a new level of technology with dual polarization radar, which allowed us to identify and see the microphysical structure, the nature of the particles that were falling as precipitation in these systems. But that's not all. We also used millimeter wavelength radars, which allowed us to see in detail the non-precipitating cumulus. The ARM program was great about providing a number of these, and they were also on the 2 ships. This allowed us to see the low-level cumulus clouds, also the non-precipitating anvil clouds. So the millimeter radars provide a great part of the picture, and we even experimented with some dual wavelength techniques to try to detect the humidity before it even turns into clouds. So we threw a lot of radar technology at the cloud population to try to document it in more detail than had been done before. And there's a lot of ideas out there, but the goal here was to try to relate the cloud population to large-scale wave properties. And in the lower row there, this is actually an idea that comes from Brian Mapes. On the lower row there, what you see is large-scale wave structure. This is not supposed to be an individual cloud. It's just the shading indicates the moisture and vertical motion distribution as time goes by and in an Eulerian sense as a large-scale wave goes by. And what we've noticed is a lot of these equatorial waves is that it goes in a sequence that's sort of reminiscent of the way a cloud behaves, with low-level upward motion at first, then a deeper layer, and then upward motion and humidity concentrated at higher levels, and some downward motion below. But all on a much longer time scale or space scale than an individual cloud system. And Brian suggested, and I hope I'm quoting him correctly, that in each of these phases of the wave favors systems going to later and later stages of their lifetime. So in the early stage of the wave, you would see a lot of convective systems truncating and not making it to their final stage, and in the later stages, you'd see more making it all the way to their ultimate growth to mesoscale systems. So the point is that the nature of the cloud population changes from one phase of the wave to another, with the frequency of occurrence of convective systems in different stages of development being different in the different phases of the wave. He called this the stretch building block hypothesis. Since my words are probably awkward, I thought he had a nice way of saying it. He's speculating, it's a hypothesis, that there's a natural selection in the atmosphere for wave packets whose phase structures produce a local Eulerian sequence of cloud zones supporting anomalies that aligns with the convective system life cycle. Anyway, just thought they were nice words. Anyway, whether that's right or not, we'll see eventually, but it's kind of guided the way we've approached the problem. And again, we're looking at the MJO over the Indian Ocean. The MJO active phase comes with phases 2 and 3, so these phases last a couple of weeks, and we had 3 of these active phases occur during this Dynamo project. And one in October, the top row, one in November, the second row, one in December, third row. Notice there's a lot of time in between these three rows that are not shown here because there wasn't hardly any precipitation at all. So these are the three rainy periods, but notice that the rain does not fall very uniformly. It comes in very well-defined, sharp pulses of a couple of days duration, more or less. And so what Manuel Zuluaga has done with me is composite all of our data sets relative to the centers of these two-day episodes. So these episodes are neither the scale of the MJO nor are they the scale of an individual cloud system. They're somewhere in between, but it's in these bursts that the precipitation seems to come. So this compositing some of the large-scale information from the ERA interim reanalysis data. Now notice that 0 at the middle there corresponds to the time of peak precipitation according to this smooth curve. So that's the center of an episode, and then it runs from 24 hours ahead till 24 hours after the peak of the precipitation episode, and large-scale data show upward motion and convergence and low-level convergence in the early stages, and then upward motion in the upper troposphere, downward motion below in the period after the 0 hour of the two-day episode. But so it looks kind of like if you were blinded to the time scale there, you might think that was the sequence of events of an individual mesoscale convective system, individual cloud system, but actually it's not. It's this larger scale structure. So what we did with the radar data is objectively identify three different categories of echo. I don't know if I can point very easily here. Yeah. The deep convective are areas where you have very intense convection defined by a reflectivity threshold that shows when convective cells are extending above 8 kilometers. Wide convective is when these intense convective echoes extend over a wide area of 800 kilometers squared or more. And then the blue are echoes that occur within systems such that the echoes have very broad stratiform regions. So you can think of these three categories as echo types that tend to occur in early, middle, and later stages of individual cloud system development. You'll see that the peak of peak frequency of occurrence of deep convective echoes occurs in the hours before the 0 hour of the two-day episode, and then the blue was skipped at the blue. The ones with the broad stratiform regions, which are the ones that are fully developed mesoscale systems, their frequency of occurrence is in the later hours after the 0 degree time, after the 0 hour time. So one more thing to look at. We also looked very larger scales. Mitch Moncrief has done that too. This shows that the MJO itself on much longer time scales has an overturning structure, which is seems somewhat similar to what you see in an individual much smaller cloud system. And if we hear what we've done with Hannah Barnes, I forgot to put her name on here, and I have done this survey of all the TRMM radar observations taken over 14 years with the TRMM radar. This is over the Indian Ocean basin, and you can see there's Sri Lanka there, kind of orient you, equator down here. This shows the frequency of occurrence of these deep convective cores, the ones consistent with earlier stages of development, and then the frequency of occurrence of broad stratiform areas in the lower panels, and you see how that changes from active phase to suppressed phase. So you see this change in the distribution of frequency distribution of different types of echoes as you go from phase to phase on this even longer time scale. So this brings me to where I want to just recap a few of the things we talked about. We've had these three great oceanic experiments, field campaigns. I've been privileged to be in all three of them. In GATE, we discovered the mesoscale convective systems were really important, and they have these heating profiles which tend to shift the heating to the upper troposphere. In Toga Core, Dick Johnson found the trimodality of the cloud distribution, and the radars with their Doppler capability in this project were able to show some details of the mesoscale circulations, which seem to go along with what Mr. Moncrief has talked about for many years. There's also some differences from Mitch, but I won't go into those. And finally, this past year, we have Dynamo and Amy in the Indian Ocean, where we focused on the convective population. We've applied, taken a multi-radar approach to the cloud systems. And we're in the midst of trying to relate these to large-scale wave behaviors. This is ultimately going to take some modeling and things for this to all work out. And I want to just end, although I haven't had time to really talk about satellites very much, they're a really important part of this picture. You saw that in the TRMM analysis that I just showed you, and earlier in the heating diagnosis we did for TRMM and how it's manifested over the whole tropics in terms of the general circulation. But in addition to TRMM has a centimeter wavelength radar which measures precipitation. In the 2000s, we've had another radar in space, which is CloudSat. I've also been lucky to be on the CloudSat science team, and as well as the LiDAR with Calypso. And these are allowing us to see the non-precipitating clouds, much like we did in the field experiment Dynamo. It's possible to see both the non-precipitating and precipitating components of the population. But it's tricky to put them together because the satellites are not in the same orbit. So for the next generation, which probably is not going to too much involve me, but I would really emphasize the importance of these satellites. We've got GPM and EarthCare coming up. This will maintain some precipitation measuring capability and some cloud radar capability. EarthCare is a European project. Megatropique provides some additional passive microwave documentation. Still, they're not in the same orbit. But really, it's not too soon to be thinking about the generation after these that are listed here. So, if we're going to continue to understand how this convection works and how it interacts with the large-scale atmosphere, we're going to have to I think, really emphasize the satellite, the reanalysis data, taking a global approach in future. So, thank you very much.
Thank you, Bob, very much. Do we have microphones? Because I can't see anything from up here. So we need questions. Yes. Yeah.
So what's the fundamental difference between the convective system, the tropics, and the mid-latitudes?
In the middle latitudes? Well, not a whole lot to first approximation. There's a lot. The mesoscale systems that form in middle latitudes are largely forming on tropical air mass, maritime tropical air masses. So you don't expect too much difference. But once you get over land, the biggest difference is really between land and ocean. And over land, the convection is more intense. You don't get as much stratiform component, and you get more electrification. So there's some real strong differences. I think and also I don't know if I mentioned this, but the systems over land are also not as wide and big as the ones over the ocean. And this is something we're starting to really see well with the A-Train data. We've got a series of papers with that where we're looking at this whole global distribution, and we're starting to get this difference between the land and ocean, and also the mid-latitude versus tropics. I think will better come out of the A-Train data than TRMM, which is restricted to the tropics.
I do have a question. The Dynamo results are very interesting, and they are over a small area, but when one looks at an OLR picture of an active period of the MJO, it extends across the entire Indian Ocean. How does one next extrapolate what you're finding on the mesoscale to the synoptic scale over the entire ocean?
Yeah, I think that's a great question, and that's what has to be approached, or what has to be addressed in Dynamo. Dynamo was not just, first of all, it's not just an observational project. It has a large modeling component. There's several global modelers involved in it. There's also people doing regional modeling, including some of my own people. And I look at these data sets like the one I just described as kind of ground truth data points, the same way you would think of ground truth for a satellite. I mean, ultimately, the big questions about the MJO have to be answered through modeling with some support from theory. But those answers are not going to be right unless the models can reproduce what we're seeing at these points where we do have these detailed observations. And we're seeing sensitivities to things like the scheme that's used, microphysical scheme that's used to represent the clouds and precipitation. We get some strong sensitivities to those things. So there's a lot I think that the data sets can do to keep the models focused and on track. Well, I'll try to repeat the question, but it was kind of long. Ed is wondering why parameterization schemes are still having, correct me if I'm wrong, Ed, having problems, and whether this is in some way related to the way microphysics are parameterized. Did I get that right, Ed? More or less. Well, Ed, you know very well that I'm not a modeler, so I'm not any more qualified to answer that than you are. But I do strongly suspect that these microphysical parameterizations have got to be straightened out before we crack some of the major problems in simulating these big events. We have seen that we have done some work over Africa where we tried 6 different microphysical schemes, and you get different answers with all. I mean, none of them are completely off, but none of them are completely satisfying either.
That seems a necessary step to me before one goes to cloud resolving models. And you still have the parameterizations at very, very small scale. Any more questions? Well, then I'd like to thank Bob very much for a marvelous talk.